myself. I'm going to talk about runaway nuclear-mitochondrial coadaptation and its effects on sexual and genomic conflict. This is work I've done in collaboration with Mike Wade, who's there in the audience. So we can both answer questions if there are more. So mitochondria are essential organelles. They're critical for the fitness of individuals, but their function is kind of like assembling a time bomb. Their successful function relies on the coordinated interaction, not just on the mitochondrial genome, but of importing products from the nuclear genome. And so you have the coordinated interaction of two different genomes that are having to work in tight, work together to produce high fitness individuals. So I'm interested in studying the evolutionary dynamics of nuclear and mitochondrial interactions and asking the question whether this tight coadaptation is ruled by genomic conflict or genomic cooperation. So Rand suggests that the nuclear and mitochondrial interactions are the most significantly co-evolved mutualism in the history of life. However, Rice points out that perhaps nothing in genetics makes sense except in the light of genomic conflict. So perhaps we have two different points of view as to what's ruling the evolutionary dynamics of this intimate coadaptive complex. So one point of view is this intimate coadaptation is the result of a couple of different processes, that you have favorable nuclear mitochondrial gene combinations experiencing positive selection and being favored, or deleterious intergenomic combinations are being selected against. So there's evidence for this kind of coadaptation from hybridization studies which break down these coadaptive complexes and result in decreases in fitness, or just the intergenomic functional coordination of having gene products that move from the nucleus into the mitochondria and working together, things like the electron transport chain and others. A different point of view on this evolutionary dynamics of this interaction is the gene's eye view, where conflict is really ruling the evolutionary dynamics. So this point of view suggests that the nuclear and mitochondrial genomes are involved in an evolutionary arms race. You have separate sexes generating intralocus sexual conflict. Different patterns of transmission of nuclear and mitochondrial genomes are generating intergenomic conflict and perhaps even sexual conflict. And from this point of view, the evolutionary influence of the dynamics of this interaction are really based on the marginal fitnesses of single genes in each genome or in each sex. So treating these as completely separate, where each genome is maximizing its own fitness at the expense of others. So to understand these nuclear and mitochondrial interactions in more detail, I built a population genetics model. So I'm looking at a diploid population, nuclear locus, mitochondrial locus. Within each of these loci, I have a very simple population genetics model. There's two alleles, big A, little a, mitochondrial locus, C and little c, and I'm exploring the full spectrum of epistatic fitness interactions. So these alleles, their combinations are generating differences in fitnesses of individuals. So rather than bore you with lots of complicated equations, what I'm going to show you next is a series of highlighted examples that explore the evolutionary dynamics and highlight some key differences based on the epistatic fitness effects. So if we start with a simple case where the A allele is seemingly good for both females and males. So I'll show you several of these graphs. And so to walk you through the first one, on the x-axis I'm listing the female or male genotypes, nuclear genotypes. So the homozygous genotypes and the heterozygous genotypes. And then the two lines represent the mitochondrial backgrounds on which those genotypes might occur. So what you see is that the big A allele has no effect when paired with a little c mitochondrial background. It's only when this nuclear allele is found in combination with the big C background that it provides any fitness benefit. And in this first case here, the big A allele in combination with big C mitochondria is providing a fitness benefit in both males and females. So it's good for both sexes. So when we have a fitness effects like this, we see a fitness synergy generating runaway dynamics. So these graphs are showing you the allele frequencies of the big A allele and the big C mitochondrial background over time, and we see that they both go quickly to fixation here. So this is a case where you have genomic cooperation. Selection is generating genomic associations between the mitochondrial and nuclear genomes, and that genes in one genome increase the frequency of the genetic background of the other genome in which their success depends. So it's not just that they both have positive fitness effects, it's that they're increasing their selective advantage by increasing that background on which they occur. And so this is generating a runaway process, much like sexual selection is generating runaway Fisherian processes. So now let's make things a little bit more interesting by adding differences between females and males. So in this case, we have the same fitness setup for females, but the big A allele on the big C background here is giving males a lower fitness. And so we have, it's slightly deleterious for males. I'm bleeding up the graphs from the genomic cooperation case, that's these green lines, but adding this new case, the blue lines. So what we saw was that genomic cooperation greatly accelerates the rate of evolution, but when we add a little bit of sexual conflict, we have differences in the effects in females and males. This is slowing down the rate of evolution. The overall outcome is the same. We still see that both the big A and big C alleles go to fixation in the population, but that process is happening at a slower rate. If we change the system and make things really bad for males, so in this case, as good as the big A allele on the big C background is good for females, it's just as bad in males. So really, just the extreme situation here. So I've left up the two previous dynamics and added this third dynamic here in the red line. And so what you see, what you see initially is what appears to be genomic cooperation between the mitochondria as it goes to fixation and the female's nuclear genome. So because of maternal transmission of the mitochondria, you see this increase in frequency of the big C background. But this is outweighed by sexual conflict between the males and females, and the spread of the mitochondrial background is proceeding, but the nuclear allele isn't changing the frequency here. So we're generating sexual conflict and genomic conflict here simultaneously. What's interesting is if you add a little bit of inbreeding to this situation, you can actually overcome this genomic conflict. So with inbreeding, these systems not only proceed faster in the mitochondria, so that's these dashed lines, but you also see the rise of this deleterious male effect in the nuclear genome. I don't have time to go into all these extra cases. The results I've been showing you are for autosomal nuclear loci, but I have looked at this in X-linked and Z-linked cases. In the autosomal case, the regions of genomic conflict are much larger than they are for regions of genomic conflict are smaller than for genomic cooperation. And the regions of genomic conflict are even smaller when you move the nuclear loci to an X-linked case and enlarges it for Z-linked genes. So the genetic architecture can really adjust the landscape of adaptation for these dynamics. So hopefully what I'm showing you here is that to understand a nuclear mitochondrial coadaptation, we have lots of areas where there's potential for genomic cooperation. And these areas of parameter space are actually much larger than they are for genomic conflict. Cooperation is spreading synergistically with runaway dynamics, very analogous to Fisherian sexual selection dynamics. And conflict is spreading very slowly. These are slow processes, and they have decelerating dynamics. So these conflict processes are actually working against themselves. So if we were to look at a natural population and try and understand the amount of variation that we see, we might see nuclear and cytoplasmic coevolution as looking as these adaptive mutualisms because of the results of these rapid evolutionary processes generating cooperation. The standing variation, so what's left over after mutation and selection balance, might appear to be conflict because these processes are rather slow. So what I hope you take away from this short talk is that there are complex interactions that can occur within and between genomes, generating genomic conflict and sexual conflict, and an emphasis on marginal fitness averages may obscure the interdependence of allele fitnesses across genomes. So that is taking the gene's eye view is going to give you, lead you down this road of thinking about evolutionary trajectories being independent of one another, when in fact genomic interactions are very important to these dynamics. I'd like to thank you for your attention. I'm happy to take any questions. That's correct, yeah.
How does having the males and females be the same individual change?
Yeah, so I'm not sure. I don't know how the dynamics would change off the top of my head. But it's an interesting question. I missed the very first part of your question.
So if there's maternal leakage?
Yes, yeah. So if there is maternal leakage, then that can reduce genomic conflict because you're kind of adding that biparental transmission there. So the model that I have doesn't actually have maternal leakage. It's a very simple way to add it, and so we have thought about it. Probably a reason to put it in the final version.
Fitness, when you're looking at sexually antagonistic, when you're finding sexually antagonistic fitness scores in the allele, what would happen if the fitness gain for female wasn't symmetrical with the loss in male, so the loss in male was large gain for female?
Yeah, so once it's equal, then that's about as bad as it doesn't get any worse, essentially. So once it's equal, then that kind of prevents, that's this case here. So any worse, the nuclear loci is definitely not increasing in frequency. Yeah.
Non-additive fitness effects? Can you talk about that at all? It seemed like your model is pretty additive, right?
Yeah, so we haven't thought about adding, I mean, I've thought about dominance and how that might affect things, but it's not in the model right now. Certainly making the math a little bit more complicated, but I'm not sure if it's generating really qualitatively